We'll turn it over to Vassily.
Uh, Thank you very much, Colin. It's really a great pleasure and honor for me to work here at this Congress. And of course, today is Lou's birthday. And really, it's impossible to uh, mm, uh, mm, overestimate Lou's impact on my work. Actually, we met Lou when I was 19. I think it was in Berlin. It was when Kontsevich got his Fields Medal. And Lou told me, well, okay, here is a new theory I created, a virtual mode theory. The paper was just submitted to the journal, and he said, well, maybe you can work on that. And maybe since then, virtual mode theory played a great role in what I was doing, and I'm extremely grateful to Lou, who was my uh, teacher, co-author, and in many areas of mathematics. And actually, in photography method, he's also a principal collaborator of mine. Okay, we are talking about birthdays. So this is Lou's talk at my seminar in the Moscow State University, and it was on May 25th, 2004. And my seminar is turning 25 soon. And Lou gave lots of talks in person, and he gave lots of talks online in many conferences, and I'm extremely grateful to him. Happy birthday, Lou. Uh, okay, and now let's go to the talk itself. So here is the outline of the talk. So first, I will tell you what the photography method is about. And then I will try to solve some equations geometrically, and I would be happy to draw equations rather than to write them. So I will be okay. Lou is here. Maybe I say again, happy birthday, Lou. Your talk at our seminar in Moscow. Uh, mm, I will solve equations geometrically, and instead of writing an equation, I will draw this equation. And then we will see that magically, just from some proper sense, as I said in Russian, из соображений здравого смысла, just without calculating, we may guess some solutions for those equations. And equations, usually they come from physics, like Zamolodchikov tetrahedron, Young-Baxter, and so on. And we may guess solutions. And those solutions give rise to invariants. Invariants of whatever topological objects. Well, and everything works for braids, and there are already lots of papers, in particular of my students, and it works for knots as well, and I will tell what to do with manifolds, and also I will tell how all of that is related to lots of areas of mathematics, just to mention some cluster algebras. Then we will see that braid groups we are all interested in act on everything. For example, I can mention that braid groups act on configuration of lines, and then there are octagon equations, rhombile tiling, gluing of cubes, and many other things. You will see some lists a bit later. And now the goal of today's talk. We're going to present a very broad way to construct invariants of topological objects. And topological objects, which are usually encoded by diagonal modular moves. And in order to do that, as usual, we solve some equations. And the equations will correspond to moves, and those can be triangulations up to Pachner moves, or maybe Diagonal modular Reidemeister moves, whatever else. And those equations will even not be written. So I will prefer to draw equations, and you will see how it works. And we will get solutions from something, and then we will check this solution by using algebra. And you see, we can be inspired by poetry, and then we can make sure that everything works by ritual property and perfected by music. What does it mean? Well, it means that we can write some solutions coming from geometry. We can guess that solutions do exist coming from geometry, like poetry, and then we make some calculations to check them, for example, using some algebra, and then having something checked by algebra for some concrete geometric measurements, we will be able to play with those measurements like variables. And if we have variables, we can create more and more perfect invariants. And then it will be related to tropical geometry, cluster algebras, and many, many other things. Okay, so since I first suggested the photography method, maybe it was in spring 2023, and I think it was in paper with Wang Jian and maybe in my paper with Nikonov. So here are archive papers. Several papers were written by our colleagues. For example, one paper is joint with Lou Kaufman and Kim Sung-John and Igor Nikonov. And also there is a paper how digraphite invariance can be expressed and explained in terms of photography method. Actually, many known invariants can be somehow explained in terms of the photography method. Well, here is some list of papers. I will comment on them a bit later. And the project was co-authored with many things, with many people. And the main co-authors are, of course, Lou and Kim Sung-John and Igor Nikonov and Wang Jian. They really made a great impact to this photography method, and with each of them I have been collaborating over years. And also, from time to time, I got very useful advices from different people. For example, Clifford Henry Tubbs, when he saw my paper on the photography method, he said, "Look, there is a paper by Fomin and Pilavsky telling that science is something what we can understand good enough in order to explain to the computer, and art is everything beyond." Victor Buchstaber, he pointed to me that whenever we whenever we see that similar things happen in different parts of mathematics, and similar equation, or for me better, a similar picture appears in different areas of mathematics, people see that one can take one part of mathematics and theorems there in order to get results for other parts of mathematics. So I discussed many things with Vladimir Turaev, Sergei Fomin, Mikhail Shapiro, because of cluster algebra as well, and many, many other people. I'm grateful to all of them. Okay, now let's pass to the photography method. So the thing we started from is that we mentioned that there is an unexpected relation between invariance of braids and three-dimensionals. Well, anyone can say, okay, we know that three manifolds close to give links, and then we can make a surgery, and then we get three manifolds. But this is absolutely a different approach. This is so I understood that that invariance of braids are invariant. Invariance of manifolds can give us invariance of braids, and it was just the very beginning. I was happy to do that because, well, I started as a topologist, but then we will see that this is related to many other areas of mathematics. So what about the photography method? Why photography? So today we will mostly concentrate on the pentagon equation, very well known in the topology of three manifolds, and coming from physics as usual. So we want to consider an object, for example, a pentagon or a two-surface, which has several states, for example, triangulations. And we want to have some data for each state. Data is a collection of measurements, for example, edge length or maybe areas of triangles, and a rule formula for translating data from one state to another. So for example, we make a flip in a triangulation, or we make a partner move, or we make some other move, and the data changes somehow naturally. And I call it photography because we can look at the same object from different points of view. So we see a triangulation of a manifold. We see one picture of this manifold, we see another picture of this manifold. But the data is good enough, so it gives us the whole information about the initial object. And actually, sometimes if the data is good enough, then when we go back and forth, and return to the initial picture, to the initial photo, we return to the initial data. And that means that our information, which undergoes some very tricky transformations, returns to the initial position. And this means that we get a solution of some equation. And here you see by data, I do not restrict myself to talk about category. I don't like talking about categories because usually, you know, if we write a textbook about something, some progress in low-dimensional topology, we should first give 6 pages of definitions, and then it's hard to go beyond. And for me, I just take data, whatever it means. It can mean edge length, it can mean angles, it can be areas. I will give some examples. I will generalize these examples and so on. So the very important example, which is both the toy model and the main example, is something called Ptolemy transformation satisfies the pentagon equation. I will pay some time to that. And actually, the pentagon equation first appeared in physics, and it turned out to be very useful in topology. So people have been used it for a long time to get three manifold invariance. And actually, then once we understand good enough that the pentagon equation, the Ptolemy satisfies the pentagon, we will see that we can use the same to get other solutions to the pentagon, for example, from shear coordinates, which appear in cluster algebras. And I prefer to draw equations rather than to write them. Why? Well, because, for example, if we want to write an equation, so what about Yang-Baxter? Some people can write Yang-Baxter like this. On the other hand, we may write them like that. Maybe up to a twist, we can use other indices. So twisted or non-twisted. those working in braids can write it like that. We can use direct sum decomposition, direct product decomposition, but we all call it Young-Baxter. Okay, so, and also we can consider tensors, groups, matrices, or just set theory. There is set theoretic Young-Baxter. So we can do lots of things. And the same with pentagon. So here it is. Here is the pentagon equation. If we have a pentagon, it has 5 triangulations. Any 2 of those triangulations can be related to each other by a sequence of flips. 2 adjacent triangulations are related by a flip. And then making a flip 5 times, we return to the initial triangulation. By the way, if we have a hexagon, the number of triangulations will be 14, and then for a heptagon, it will be 42, and then there will be Catalan numbers, if we talk about numbers. And there is a very nice structure of associahedra, which were invented by Stashev, and which are ubiquitous and are related to many parts of mathematics. Okay, so it is the pentagon equation, but where is the equation, and what are our, what do we want? Actually, here I want to put data inside this pentagon. And I want to have some data transformation rule here, for example, at this edge. And for each flip, I suggest a transformation of data. And I want to, I want this transformation to satisfy the condition that after 5 steps, I return to the initial data. And in my case, the Ptolemy transformation means that if I have a quadrilateral here and put side length to that quadrilateral and 1 diagonal, then when I flip the diagonal, the other diagonal gets y, which is equal to AC plus BD over X. So this is my transformation of data, and you may play with some other data and some other transformation rules. And that's my first example. Ptolemy satisfies pentagon. And you see by data, for data, you can take maybe not edge length, but areas of triangles, or maybe angles, or whatever you prefer. And it may be not just a triangulation, it may be a triangulation of something higher dimensional, or a diagram, or whatever else. And you can look for something meaningful. And then from geometry, you can guess some data transformation rules. And that reminds me a lot the general setup of cluster algebras. When we have some data, and we have some quiver, and we have a seed mutation, and after several mutations, we return to the initial position. And actually, those who know cluster algebras know this example very well, that Ptolemy satisfies pentagon. And this is related to seed mutation. And actually, the pentagon equation, saying that the composition of 5 transformations is identical, is ubiquitous because it appears in different parts of science under different names. I suggested to read the book by Girfan Kapranov Zelevinsky, beautiful book about combinatorics, topology, categories. And as for groups and other things, braid groups, I suggest our book Invariants and Pictures with colleagues in 2020. Okay, so recently, but it was in 2023, I saw a beautiful paper by Anna Felixson, Ptolemy Relation and Friends. And she said that cluster algebras are ubiquitous. They are important in mathematics because they are related to, and here you see a beautiful flower, Coxeter groups, tropical geometry, and many, many other things. And that's why we can motivate ourselves by problems from other areas of mathematics and solve problems from other areas of mathematics by using cluster algebras. And now I want to argue that the photography method will be ubiquitous because we can draw a similar flower, what it is related to. So it's related to cluster algebras. It's related to tropical geometry. It's related to Stashev polytopes. It's related to triangulations of surfaces and manifolds. It's related to invariance in low-dimensional topology. And also, it is related to many theorems from school geometry, like Desargues theorem, Pappos theorem, and other things, which allow us to get easily invariance of topological objects we like. Okay, so now what about braid invariance? I want to construct braid invariance by using a solution to the pentagon equation. So here is some know-how. By pentagon, I can use whatever I want. It can, by pentagon equation, by data, I can mean whatever I want. It can be a tensor, a matrix, well, maybe a quiver cluster algebras, whatever else. And importantly, the solutions to the pentagon equations, which are known to be lots. So, for example, Q minus J symbols, which appear in three-manifold invariants, they give rise to invariance of braids. And this is a novelty. And in order to get to braids, I will have to pass to the notion of Voronoi diagrams, which relates braids and pentagon. Actually, already at this stage, I got lots of invariants of braids, which appear from many black boxes I can take from various solutions to the pentagon for three manifolds. For example, there is a beautiful book of Luke Kaufman and Sosthenes Lins about recoupling theory, and recoupling invariants also give us braids. Okay, now we look at a braid as a motion of endpoints of the plane on the plane as usual. So if I have endpoints moving on the plane, I'm interested in those situations when those points are generic, meaning that I want to tile the plane into pieces, and each piece here is the set of points which are closer to its center than to any other center. So I have Zi and I have Zj, and my Ui is, oh, maybe I shouldn't reverse the sign. So Zi is closer to Z than to Zj. And so here is a picture. So we have capitals of some states, and the state itself contains of those points which are closer to its own capital. And generically, it's a graph, maybe with infinite edges, of valency 3, and the dual graph is a triangulation. Well, never mind the infinite point. And as points move, those triangulations undergo flips. So typically what can happen is that 4 neighboring points are on the same circle, and the triangulation undergoes such a flip. So a flip is a piece of movement, is something which we want to associate some data transformation to. And this is an event of codimension 1. And the main principle, which can be used in many areas of topology, is that generators of our transformation group or whatever else correspond to codimension 1 events. And relations should correspond to codimension 2 events. And in our situation, we want to have data transformation rule corresponding to flips, so that after 5 flips, this data transformation rule returns me the initial data. And you see, I want to construct an invariant of braids. How do I do it? Well, I take a collection of points. May this collection be generic. I have a triangulation for this collection of points. And I associate some labels to edges of the triangulation. And as points move around each other, then if points move around each other, the data changes. I return to the initial position and I get a new data. So with a pure braid, I associate some data transformation. And this should be an invariant if some condition holds. Which condition? Actually, the pentagon. Why pentagon? Well, the pentagon, because of the following. Assume we have 5 points almost on the same circle. If I have 5 points like this, then they can move a very little bit, staying almost on the same circle. But if they move a very little bit, there is no braiding. And if there is no braiding, then we have to associate a trivial transformation to such a sequence of flips. And in particular, it may happen that my pentagon triangulation, Delaunay triangulation, undergoes 5 flips in a sequence. And this is the pentagon equation. Actually, there are some other equations, but they are not as important. Now, if we have anything which satisfies the pentagon equation in whatever form, it gives me braid invariance. And so here is an algebraic way of checking that Ptolemy satisfies pentagon. So you see, I take edges of the pentagon plus 2 diagonals. And whenever I perform a flip, for example, here, I replace one diagonal called Y with another diagonal called Z. I use the Ptolemy transformation Z equals XD plus C over Y. And I do it 5 times, and magically, I return to the initial position. Why magically? So as Vladimir Arnold used to say, I can prove it, but I don't understand why. And actually, the real explanation is that is the photographer method. Well, actually, the real explanation is as follows. So if we have an inscribed pentagon, it has some data. It has edge length and diagonal length. And this data knows everything about all diagonals, about all diagonals, once forever. And this means that whatever way I go, I will return to the initial position with the same data. And you see, there is nothing to prove, there is nothing to check. On the other hand, we get some nice equations, nice solution, and an invariant of braids. And now you see, this is a way how one can calculate this for a non-trivial braid, and it can be found in my book. Also, you see, just by using logic, I can make many solutions for free. So I said that Ptolemy satisfies pentagon, right? And now there is a work in progress with my student Gurnor Singh that the same works for through the tropical analog of Ptolemy. And for tropical analog of Ptolemy, it is meant that I can work over any semi-field, in particular over any tropical field. So you see here, all my data transformation rules use only addition, multiplication, and division, no subtraction. And if I make 5-step transformation, I return to the initial position and I get an equality between two Laurent polynomials with positive coefficients. So actually, the equation I'm solving means that I have two polynomials which are equal. And these polynomials have no minus signs there. And this means that I can manipulate with addition, multiplication, and division with no subtraction. And this means that just logically, I can see that it works for tropical semifield. So you see, I guessed something geometrically. Geometry gave me an idea. Then I can prove it by algebra. And then I can enjoy doing some logical things. Well, for example, I can forget that my x and y are length. They can be free variables, or I can take semi-fields. I can take whatever else. And this gives me brain invariance. Well, later it gives not invariance, but I'm not going to talk today about that. Well, you want more examples? Right. So you see, I use the formula for an inscribed quadrilateral. For an inscribed quadrilateral, we have Ptolemy, AC plus BD equals XY. And what about any arbitrary quadrilateral? Well, there is a beautiful formula which is published maybe in mathematical American Mathematical Monthly or something like that. This beautiful formula expresses the other diagonal in terms of ABCD, but it's very huge. It contains lots of square roots. And if we try to apply 5 times, well, it's beyond my computer, for example. It has too many square roots. But if we have this formula for data transformation rules for one flip, and we apply it instead of AC plus BD equals XY, if we apply it 5 times to the triangulation of the pentagon, it will return us the initial data. Why? Well, just because if we have a pentagon and 2 diagonals, this defines everything. Well, of course, here you can say that triangle inequalities play some roles, but it's a minor thing. So you see, even without knowing this formula by heart, I can say that whatever this formula is, it will give me a solution to the pentagon and a braid invariant. Similarly, let's do it for the spherical space and hyperbolic space. Oh dear, for hyperbolic space, I need hyperbolic sines and cosines. For spherical case, I will need sines and cosines. And formulas are even more terrible, but they will satisfy pentagon and hence give me braid invariance. Well, why only length? Actually, we can take some other data. For example, if we have a quadrilateral, we can take 3 angles here, and angles can define my quadrilateral up to similarity. And again, we can write down transformation and guess that it satisfies the pentagon. Now you see that it should work in a much larger context, and this is the essence of the photography method. Okay, now one more thing, shear coordinates. It's known very well that there are shear coordinates for ideal triangulations, and I think cross ratios and some other things in hyperbolic geometry. So we put some data on edges of a triangulation of the 2 surfaces, and when we undergo a flip, we flip edges and we change the data like this. And again, this data, there is some geometry beyond this data transformation, And this geometry guarantees that if we return to the initial position after 5 flips, we will get the pentagon equation. Also, there is something called power commutativity. I don't want to talk about that. And now one more thing, how we can extract invariance of braids. Again, we take one part from one thing from one part of mathematics, another thing from another part of mathematics, and just say, okay, it will give an invariant. This is just a black box, but it works. So take a solution to the pentagon equation. Which one? Well, there is a recoupling theory for getting q minus 6j symbols corresponding to, design for 3 manifolds. And if we take such things, we will get some matrix, a solution to the pentagon equation. So we make some flips like this, and we put some labels, and we get matrices, and it will satisfy the pentagon. Hence, it will give me invariance of braids. And this is done in my paper with Igor Nikonov, even prior, even before I formulated the photography method. Okay, well, now Igor Nikonov and myself, we are working on knot invariance out of braid invariance, and actually we want to close up the data transformation from the top to the bottom. So if we have a braid, we get some information going from the top to the bottom, and it is invariant, so we can get any solution to the pentagon. And if we close the top, we can get a knot invariant. This is a work in progress. And actually, some words can be said about invariance of 3 manifolds. This is a joint project with Lou, Igor, and Kim Sung-Jong. Well, actually, here I just say about similarity between pentagon, Pachner, Matveev, Piergalini, and many other things. I'm not going to formulate theorems. Just look at the Matveev-Piergalini move when we have 2 butterflies. We have butterflies. This is a spine of the 3 manifold, and we have a picture like that. So here we have two true vertices. Here we have 3 true vertices, and we have 3 wings. And this is the main equation. This is the main thing in the main move in 3-dimensional topology. 3 plus 2 equals 5. And other people can look at that dually. So we have a bipyramid, which is split into 2 tetrahedra, and we can split it in 3 tetrahedra in another way if we remove one face, and instead of this face, put one edge and get 3 wings, 3 tetrahedra. And I just tell about the similarity. I don't have much time to talk about that. This similarity gives rise to ideas which lead to invariance. One more thing is that Dijkgraaf-Witten invariance can be explained in terms of the photography method. Well, actually here, Dijkgraaf-Witten invariance, for example, of 3 manifolds, can be defined as follows. So we take some group, we take some triangulation of a manifold, maybe 3 manifold. We put some data on edges, some group elements of edges, and we put some data to triangles. So we put data on 1-dimensional objects and on 2-dimensional objects. And then we suggest a data transformation rule. And this data transformation rule is natural geometrically. For example, if we use edges, then it satisfies the condition, the product condition. If we here have A, B, and B here, then this edge will receive A times B. So this is multiplicative. And the condition for two simplices is some cocycle condition, whatever it is, and it's again natural. And if we have some naturality, then one immediately get that some formula will be invariant under move. So in our case, it's the Pachner move, the 2-3 Pachner move, and naturality is very similar to what we had in Ptolemy yields pentagon. Importantly, here by data, we mean elements of groups. And importantly, here we have two pieces of data on edges and on simplices. And we expect that similar things will work for Crane-Yetter invariants. And here in maybe one of slogans that everything works for de Graaff-Witten is that a cocycle can be thought of as a volume. So you may think of a simplex, and if we assume that this simplex of dimension n+1 completely lives on a hyperspace, then the sum of areas of its subsimplices of codimension 1 taken with appropriate signs gives 0. So somehow it's the cocycle condition. So somehow cocycle is volume and volume is 0 is enough to get a cocycle condition satisfied. Okay, now I want to say about work in progress concerning invariance of arbitrary dimension. And so now I tell how to get more and more solutions and to get more and more evidences of the photography method. Okay, assume we have a manifold and we triangulate it. We consider a manifold as an equivalence class of triangulations modulo Pachner moves. And I want to associate some natural data triangulations and data transformation rules for Pachner moves. For example, 2-3 Pachner moves. And let me say that my data will be volumes of triangles. Well, not triangles, but tetrahedra. So I want to associate volumes maybe in quotes, because this can be some volume formula for Euclidean geometry, hyperbolic geometry, or something like that. So I put some information on edges, and I take a volume formula, whatever it is. And now I want to give a tautological lemma, which is crucial for getting an invariant. You see, assume we have a bipyramid. We can split it into 2 tetrahedra like this. Or we can split it into 3 tetrahedra like this. And then statement. The sum of those 2 volumes is equal to the sum of those 3 volumes. Agree? Now, if we take, if we put labels on edges here, we can use some formula, for example, the Kelly-Menger formula for the volume. And if I have this bipyramid, then in terms of the 9 edges, I can calculate the other diagonal. Oh dear, this formula would be extremely huge. But then I apply the Kelly-Menger formula 3 times again. And the photography method says that the sum of those 3 volumes in formulas will be equal to the sum of those 3 volumes. Doesn't it remind you anything? Sum of 2 equals sum of 3. Well, it can be used for getting invariants under 2-3 pattern moves. And you see, this can be logically extended to any dimension. So we can do it for any dimension, such things, to get pattern move invariants, and then take state sums and so on, okay? Well, some words, as our talk is closing to the end, some words about further references. Well, initially and prior to all other work on the photography method, we, Igor Nikonov and myself, found this paper of Liu and Sostenes Lins and used the recoupling theory to get an invariant of braids. Well, pure braids, it's just a technicality. An invariant of braids coming from something with manifolds. Well, in this book, there are lots of dreams about picture-valued invariants, and actually this calculation of Ptolemy yields pentagon was first mentioned. And here is the beautiful paper by Kaufman and Lins. Here is a diploma of my student. Actually, I can go and to the infinity and tell about many other papers and many other directions. But now I want to concentrate on some further directions of research, which are important from my point of view. And I want to say that many equations and data transmission equations are ubiquitous and relate many areas of mathematics. You saw that the pentagon appears at least twice in 2 different parts of low-dimensional topology. I'm pretty sure that Reidemeister or Pachner or whatever else moves we use and love in knot theory will appear everywhere else. And also, this pentagon can be done at any level. So recently I was talking to Michael Shapira. It should give invariance in cluster algebras. And then just look at that flower where I said that, for example, pentagon is related to everything. So we may expect that we can get Conway-Coxeter-Friese patterns, Greenfield associators, tropical geometry. Something is done in this direction. Maybe 20 years ago, 25 years ago, we were all fond of categorifications. We were trying to categorify and follow Khovanov and categorify all invariants of everything. We were talking about categorification. Then spectrification came to topology. But now you see, if we see that many parts of mathematics are related to each other, we can dream about tropicalization, clusterization, Friesifications, and so on. About concrete, talking about concrete invariants, well, I think we did De Graffiten. Why don't we do Crane-Yetter? I expect this is doable. And also, we were talking a lot with Kevin Walker, and he suggested some universal state sum formula, and I think universal state sum formula will have to do a lot with our photography method. And also, well, geometrical invariants via photography method, gluing cubes, rhombile tilings. This is something already written in the last 1.5 years. And not only pentagon, I can mention octagon relation and something else, which is already solved by using the photography method. Many other things are already done, and many other things are still to be done. And I think I want to wish happy birthday to Lou and thank everyone for the great organization of this conference. And I think my time is up. I'm finishing.
Great. Thank you, Vassily. That's great. I'm going to turn off recording.